Hello, this is Archit's test corrections for the WEP post-node mini test. So we can go to problem number 1. So I got this wrong. It says the work done by gravity during the descent of a projectile. I put it was positive since I thought it depended on the sign for the y-axis. So I thought if up was y and then work would be negative, and if down was y, it'd be negative. However, work is just force times distance. So the force is gravity in this case, and then we can multiply this gravity by the distance it fell. So in this case, you're going to have work that's always going to be positive. Okay, so we can go up to number 2. And this is because like the force, and if down, let's say if down is positive or if down is negative, that means your distance and your force is negative, and they're going to cancel each other out, right? So that's why it's going to always be positive. So let's go to number 2. A particle starts from rest at time t equals 0 and moves along the x-axis. If the net force on the net force on it is proportional to t, its kinetic energy is proportional. The actual answer is t to the fourth, because if you integrate it, you get t to the fourth over 4, and you get t to the fourth. So we can go to number 3. Number 3 says a 1.5 kg crate falls from a height of 2 meters onto an industrial spring scale with a spring constant of 1.5 times 10 to the 5th Newton meters. At its greatest compression, the reading on the scale is... So the way to answer this question is we can find the velocity at which the block lands using kinematics, right? So we can use equation, equation 5. V0 squared plus 2a delta x to solve for your final velocity as it lands onto the scale. And then once we do that, we can use conservation of energy. So half mv squared, all the kinetic energy transfers into spring potential energy. So we have half mv squared equals half kx squared. And then doing this, is the halves cancel out. We're left with mv squared equals kx squared. And since we know mv squared and k, we can solve for mv squared over k equals x squared, and then take the square root of both sides, and we have the square root of mv squared over k. And plugging in numbers, you get 3.02 times 10 to the third power newtons. Okay, we got number 4 right. Okay, at number 5, a crate is initially at rest on a horizontal frictionless table. A constant horizontal force F is applied. Which of the following 5 graphs is the correct plot of work W as a function of crate speed V? So, as force is being applied, the velocity is increasing. The velocity is always going to be increasing, right? And since work is force times distance, and if you have a greater velocity, and if your velocity is increasing, that means your distance also increasing, but at an exponential rate. Since your velocity is increasing at a linear rate, your distance has to be increasing at an exponential rate. So in this case, when you plot work on the y-axis and velocity on the x-axis, we have to get an exponential curve instead of a linear curve. So that's why the correct answer is the one displayed over here. Okay, so let's go to number 9. So 2 objects with masses m1 and m2 have the same kinetic energy, and both are moving to the right. The same constant force is applied to the left to both masses. If m1 equals 4m2, the ratio of the stopping distance m1 of m2 is... So since they have the same kinetic energy, their stopping distance remains the same, since the same amount of work is needed to stop both of these masses, since they have the same kinetic energy. And since we know work is the change in kinetic energy, the same constant force is going to be applied to both passes. So that's why the ratio is going to be 1:1 instead of 1:to anything else. They're going to be the same. So let's go to number 10. So at 10, at time t equals 0, a 2 kg particle has a velocity of 4 meters per second minus 3 meters per second j. At t equals 3 seconds, its velocity is 2 meters per second plus 2 meters per second. Okay. So on this problem, they didn't show components for I and j, so I just assumed it was 4 minus 3 and is 1, and 2 plus 3 is 5. Whereas you can take the j component over here, and then you have, since work is just the integral of momentum, what we have to do is to just find the change in momentum, right? So we have 2 times negative 3, that's initial momentum, which is negative 6. And then we have 2 times 3, that's your final momentum, which is going to equal 6. So what's the change in momentum here? We have 12, and that's going to be our work done. Okay, so let's go back to this. Okay, let's go back to our last two problems. So in raising an object to a given height by means of an inclined plane as compared with raising the object vertically, there's a reduction in, so I put force required. I put value of the acceleration due to gravity. However, gravity stays constant and does not change. I thought the y aspect of gravity. However, I did not include the x aspect of gravity, the horizontal aspect of gravity in my answer. That's why I put that. So the actual answer is force required. So as you know, since you're to push the object up a certain vertical distance, you don't have to use as much force since you're not repelling against mg. Since the opposite force is not mg but rather mg cosine theta or mg sine theta. So this is it's gonna be mg sine theta. So it's gonna make it much easier as the sine theta is going to decrease the total value of the vertical force. And then 1 watt is, I made a silly mistake here. I thought it was just 1 kg times meter per second cubed. But once you take care of the units, you are supposed to get 1 kg times meters squared over seconds cubed. Yep, so this is my test corrections for WEP post-note mini tests, which was taken after the notes.